In transport phenomena courses, we talk about mass flux. And mass flux, if you're already familiar with heat flux, deals with very similar concepts. We have some kind of driving force, which in this case is nothing more than a difference in concentration between 2 points of a particular solute, and we have some kind of diffusion coefficient. And so what I'm going to do in this video is work through an example problem that will introduce something called the Sherwood number in our calculations. And with the Sherwood number, we're going to be able to determine the mass transfer coefficient. And given the concentration difference between 2 points, we're going to be able to find the rate of mass flux of a salt that has been deposited on the walls of some tube into a bulk fluid that we are flowing through it. And so if you think you can solve this problem right now, pause the video and we're going to be working through it now. And so the very first thing to recognize when you're dealing with these problems is the importance of Reynolds number. And Reynolds number right here dictates whether or not we are in the laminar or turbulent regime. And the sets of equations that we're going to use are all going to be based off what Reynolds number we have. In this case, Reynolds number is 40,000, and in general for fluid flow through a pipe, if Reynolds number is greater than 10,000, we are considered to be operating in the turbulent regime. And so now that we know that we are in the turbulent regime, we can turn to one of the Sherwood relationships that tells us this. So we have our Sherwood number is equivalent to 0.023 times Reynolds number, quantity raised to the 0.8 power, times our Schmidt number raised to the 1/3 power. And intuitively, the Schmidt number, to add some background here, is the ratio of our boundary layer thicknesses, because we're going to have a hydrodynamic boundary layer as well as a concentration boundary layer within our bulk fluid. And so the Schmidt number is what's giving us this relationship. And so what we're going to do first is calculate what our Sherwood number is, and what we will find after we plug and chug our values is that our Sherwood number comes out to be 189. And note here, there are no dimensions because Sherwood number, Reynolds number, and Schmidt number are all dimensionless quantities, and you're going to be dealing with a lot of dimensionless quantities in a transport phenomena class. The next step we're going to be taking now is making use of the definition of what Sherwood number is, and that is equivalent to Km, our mass transfer coefficient, times the diameter of our pipe divided by the diffusion constant of the solute, which in this case is our salt buildup, into our fluid, which I call big D. And so with these values, we were given our diameter, we were given our diffusion coefficient, and we now calculate our Sherwood number so we can solve for Km. And so now if we actually plug and chug, what we will find is that Km has a value of 6.3 times 10 raised to the minus 4. And at this point, Km is not a dimensionless quantity. Km will have units of your diffusion coefficient, which had units of centimeters squared per second. And we're going to be dividing it, because we're dividing by the diameter, by 1/centimeters. So Km, to emphasize, is equal to 6.3 times 10 to the minus 4 centimeters per second. And I can't emphasize enough how important it is to keep track of your dimensions when you're working with these problems, because oftentimes you're going to be asked to give your answer in forms of meters or centimeters. So you need to remember what your units are before you move forward. And so now that we were given and we have derived what our mass transfer coefficient Km is, we can turn to our our mass flux equation. And our mass flux is equal to our mass transfer coefficient Km times delta C, where delta C is a difference in concentration. So Km times, and then C at the surface, minus C bulk. And so this C surface quantity is equivalent to the solubility of the salt in our liquid. So what we are doing right now is assuming that at the interface, so if we were to zoom in right here to where we had our little salt buildup in our actual fluid, we're saying that at the interface where, like if this was our radial axis and we're looking at R, we're saying when R is equal to big R, which is the total radius, at the interface between the salt and our fluid, that is saturated with as much salt as it can possibly get to, because we've reached an equilibrium at that interface. And then in addition, and I probably should have said this in the problem statement, but we're going to make the assumption that our bulk fluid, the fluid we're flowing through this, does not have any salt in it already, so we can neglect the bulk fluid concentration. Now you can't always do this, and if we were dealing with a problem that wasn't at steady state and we had concentration profiles that were evolving over time, the math will get a lot more complicated. But for the sake of introducing the Sherwood number and calculating mass flux, we're going to make this nice assumption that our bulk fluid does not have any salt in it, and therefore we can neglect this quantity. And so at this point, it's really just evaluating these terms. So we know that our mass flux was 2 times, so this quantity will be equal to Km, which was 6.3 times 10 raised to the minus 4. And then keep track of your units. We're going to have centimeters per second. And we're going to be multiplying this by our solubility, which is really our surface concentration of the salt. And this was 2 times 10 raised to the minus 4 mole per centimeter cubed. And note how our solubility has units of concentration, because it's basically telling us if I had 1 liter of water or a cubic centimeter of water, how much salt can I diffuse into that cubic centimeter of water before I start realizing a precipitate? When do I start seeing the salt crystals reforming because I can't put any more in? Continuing, if we now calculate for what our mass flux is, we will find that it has a value of 1.3 times 10 raised to the minus 7 mole per centimeter squared per second. And going back to what our definition of mass flux is, we know that flux is any quantity per area per time. In this case, we're dealing with moles per area per time, moles per square meter, per square centimeter per second. And another thing I would like to reiterate here is sometimes you'll get curveballs on exams and they're going to ask you to give your mass flux in terms of moles per square meter per second. And so if we wanted to do that, it would be as simple as multiplying it by the appropriate conversion factor, which in this case we'd have 1.3 times 10 to the minus 7 mole per centimeter squared per second. And we're going to multiply this by, so we know that there's 100 centimeters in 1 meter, and then because we're doing with square centimeters, we're going to square every quantity within these brackets. And if we do that, what we would find is that this would be equivalent to 1.3 times 10 raised to the minus 3 mole per square meter per second. Okay, and so to recap, what we did in this problem statement was first ensure that we were working within the turbulent regime, because we were able to apply this particular Sherwood relationship because we were operating within the turbulent regime. And after we did that, we were able to use our Sherwood number and the very definition of Sherwood number to calculate what our mass transfer coefficient is, Km. And we were already given every other quantity, so once we got Km, and we were able to determine and assume that our bulk fluid had no concentration of salt in it, and we also made the assumption that at the interface between the salt and our fluid, it was saturated with salt, we were able to actually calculate our rate of mass flux, and all the while we are keeping track of our units so that we don't make the mistake of being orders of magnitude off in our final answer. And so that's going to wrap things up for this video. I hope you guys find it useful, and thanks for watching.